Yeah, we're going to be working on experiment 4.5 called water's cohesion. And by the way, I think I figured out how to get Zoom working so that there's not going to be this constant like getting booted out that's been going on. There's a couple of different ways to enter the Zoom meeting. And if you enter not with a link, but by saying, clicking on join meeting, and then you enter the meeting ID, which is going to be like the name of your classroom. Like this one, the meeting ID is just going to be kids praise as one word. Then looks like you can actually get in consistently, whereas with a link, it almost never let me in. So from now on, hopefully, if you're absent during class, you can actually zoom in to the class while it's going on rather than what's generally been happening, which is the beginning of class. I try to do that, it doesn't work, and then I record locally and load it up to YouTube afterward. So, but if you ever try to zoom in and it's not working, first of all, just see if I'm actually logged in, like if there's two participants, then if I'm not actually streaming, it might be because we're taking a test or something that I don't need to stream. But if you ever can't make it in for whatever reason, whether because Zoom isn't working or any other reason, then just know that when the school day's over, I will email you a link to the class video that I've uploaded to YouTube. That's what I've had to do these past couple of weeks anyway. So, Bo, you had a question?
I was just wondering if you could answer a question for the testing server instead.
There's somebody who's not done who's watching online, so no.
Okay, never mind.
Yep. Okay. All right, so this is a pretty fun experiment. Water's cohesion. So the research question, will an object floating on water keep floating if you take away the water's cohesion? Here's a definition of cohesion. It's the phenomenon that occurs when individual molecules are so strongly attracted to each other that they tend to stay together even when exposed to tension. And if you're talking about cohesion on the surface, what do we call that? Surface tension, yes. Okay, now we need to talk a little bit about how water works. If I have an oxygen atom, is that positive, negative, or neutral? And if I have a hydrogen atom, is that positive, negative, or neutral?
Neutral.
Why are you saying neutral?
Because they each have one proton, one electron, and like one neutron.
Yeah. So it turns out that if it's an atom, the charge will always be neutral because however many protons an atom has, it's going to have an equal number of electrons. And the positives and the negatives cancel each other out. So how many protons, you can look at the front cover of your book, do we have in hydrogen? Annalise already basically told us.
One.
And so you got one proton, so I'm just going to draw a plus sign there. And then how many electrons would be orbiting around that? One. So protons are a positive one, neutrons are a negative one. They cancel out, they're neutral, these hydrogen atoms. What about oxygen? 8, good. All right, so I'm just gonna not worry about the number of neutrons. I'm just gonna draw 8 protons inside. And then we need 8 electrons orbiting around that. So it'll be 2 out there and then 6 out there. All right. And then we know that there's a chemical bond between the protons, or sorry, the hydrogens and the oxygen, because if it's a molecule, they're bonded together chemically. And the chemical bond is not incredibly hard to break. When we did electrolysis with the battery, just 9 volts of electricity, we were able to split this molecule, break the chemical bond so that we had oxygen floating off and hydrogen floating off as gases. All right, so if this were charged, by the way, like for example, if anywhere in one of these atoms, like let's say one of the atoms lost an electron, then what would we call it at that point?
Imbalance.
That would be true, yes. Oh, what else? Ion, yes, very good. So when an atom is given a charge, it's no longer an atom, it's an ion. All right. It turns out that water is something called polar. It's a polar molecule. And what that means is that one side is always going to be slightly negative, and the other side is always going to be slightly positive. But wait a second, didn't I just say that this is a neutral molecule? That these atoms are neutral and then the molecule will be neutral? So how could that be? How could it be that one side is slightly positive and one side is slightly negative? And I'll give you a hint. It has to do with not the number of electrons or protons, because there's going to be 10 protons and 10 electrons in this, but it's going to be about how they're shared. All right. So any ideas then? How one side could be slightly positive and one side could be slightly negative? All right, so when these electrons are orbiting in the molecule, what ends up happening, I'm going into more detail than the book does here, but they will kind of orbit around the different atoms in it. So let's just say you have this, like, let's just focus on one side of it. Big atom, small atom. And you got an electron orbiting around. Which one, the big one or the small one, is the electron going to spend more time orbiting around? Why?
Because it's bigger,
Yeah,
so there's more room
Yeah.
to get around.
it's all about the circumference, basically. So if you were to go around this part of this one, that's a pretty short distance. You could stretch it out to be something like that, maybe. But then you orbit around, you know, most of the circumference of this one, stretch that out, it might be a lot longer. So each of the electrons are going to spend a longer amount of time orbiting around the bigger atom than the smaller atoms. As a result, at any given moment, you're going to have more electrons on the oxygen side, making it slightly negative. And you're going to have fewer electrons on the hydrogen side, making it slightly positive. Does that make sense? And we call this polar. A polar molecule is one that has an imbalance of charges. So it's still neutral overall, but one side is slightly positive and one side is slightly negative. Questions so far? That little characteristic of water is actually going to be responsible for most of its qualities. So if you get anything in this entire module, make sure you get that. And what does this mean for us? I think I'm going to go ahead and erase this and make some smaller ones. When water molecules are near each other.
John, can you stand a little bit of that when you draw?
Over here?
So, yeah.
Okay.
So we can't see where. Thank you.
So if you have, let's see, am I blocking anyone on this side? No, okay, that's good. The water molecules are slightly negative on one side, slightly positive on another. Then when they come in contact with other water molecules, what happens if you have a positive and a negative charge of something near each other?
An explosion.
Nope.
They're
Well,
no, they attract.
they attract, yes. So like charges repel each other. But a positive and a negative together will attract. What this means then is when you have water molecules that are close to each other, then the hydrogen side of one molecule and the oxygen side of another will attract to each other. It's actually the same force that's used in magnets. It's the electromagnetic force. This is an electricity kind of a manifestation, but it's also the same force that has a magnetic attraction. So they behave like magnets in that way. This is actually why water stays a liquid at room temperature. It's because in liquid form, it's pretty hard to separate water molecules from each other compared to other substances because they are attracted to each other. And so this is what gives cause to cohesion. Cohesion, again, is when individual molecules are so strongly attracted to each other that they tend to stay together even when exposed to tension. So imagine like, have you ever made like a kind of like a bridge out of magnets, like a whole bunch of magnets linked together, and then you like, stretch it across something and put weight on the middle. And if you haven't, you could probably imagine doing that, right? So you got like a, I don't know, here's, and then you got a bunch of magnets, and maybe you like secure them on either side with some weight or something. And then if you were to put something in the middle of it, like a cow. Then what's going to happen to those magnets? Yeah, it's all going to bend downward. But if they're strong enough, they'll stay together and everything's just going to sag. That's what actually happens at the surface of your water. And so when you put something on the surface of the water, then you ever seen like a water strider, for example, a little insect that kind of like darts around on the surface, or a whirligig? The water around them will kind of bend downward, but they can stay on top because they're light enough that the attraction from one water molecule to another is enough to keep it up. But then, of course, if the cow was too heavy, or if you somehow got rid of the magnetic attraction, what do you think is going to happen? Yeah. So that's what this experiment is about. We're basically asking, if we put something floating on the surface of water, like in your bowls, we're actually going to float a paperclip on your bowl. And then if we can somehow get rid of the cohesion in the water, then what do you think is going to happen to the paperclip? This is your hypothesis now. Think it'll sink? All right, so specifically what we're going to do is we'll float the paperclip, and there's a technique to do that using the toilet paper and some magic. No, not really. But the way that you could break water's cohesion is actually to put something else in the water that the molecules are more attracted to than each other, or at least as attracted to as each other. So we're going to take the dish detergent, which I have over here, and after we get the paperclip floating, just stick a little drop of dish detergent in the bowl and see if, and also how quickly, the paperclip will sink. Does that make sense?
Are we gonna do anything with the toilet paper?
Yeah. So the back table, by the way, doesn't have a bowl. We didn't have enough, but we didn't want to bring like great big glass ones. So you guys can split up among the other tables however you want, and watch each table. So if you could open up to experiment, whatever this is, 4.5. If someone could find the instructions about the toilet paper and tell us what to do about that.
Tear 1 square toilet paper.
Done.
Rectangle out of that toilet paper. It should be 2 inches longer and 2 inches wider than the paperclip.
Okay, great. So you could just approximate. It doesn't have to be exact. But I brought some scissors. And so 2 of the tables have the scissors. So roughly 2 inches, then wider and longer than the paperclip. I'll go ahead and do this in front of the camera. So paperclip. And if I were to put it in the corner, need about 2 inches on either side. So something like that. And 2 inches longer as well. So about like something like this should do. And now yours is done. So do you have scissors, or do you have scissors? Okay, you have scissors. Great. So go ahead and cut the toilet paper around the paperclip. Who wants me to film their particular one? I'm going to film one of them. You're right here, so any objections? All right. So let me know. Man, that looks really far away. That looks good.
Maybe tilt it up a little bit more, that way you can see what we're doing. or down, like just right there.
Okay, that good?
Yep.
Good, thanks. All right,
Hi, Emily.
What is that?
I don't know.
Hey.
Hi.
Hi, Sarah.
Hey. Hi, Sarah.
Okay, is everyone ready? What you're gonna do is put the paper clip on the middle of that little bit of toilet paper that you cut, and then lay the paper gently across the middle of your bowl, like so that it's floating in the water. And what should happen is the toilet paper will sink, but the paper clip will stay up.
Is the toilet paper supposed to sink all the way? Oops. Okay. Oh, dang.
Looks like they went together.
Were we supposed to put the paper clip in the long ways of the toilet paper?
I guess that would help, yeah. But all right.
Thank you.
You can cut another piece. While you do that, I'm going to see if I can do this.
Oh my gosh.
Where are the scissors?
They have some fish like that.
Oh, I can do another scissors. Annalise and Kate, could you hand your scissors to? Actually, it looks like these are coming. Thanks.
I'm guessing that didn't work as planned.
No.
That's funny because here they both sink. Okay, this looks like it's going well because you can see the more that you see the water, like if you see it bending, then that means there's some good cohesion
Looks
going
like
on.
it's going.
Very good.
Yes!
All right.
Why am I so excited? I don't know. Look how much
It's
floating. Oh my gosh. Best thing ever. Yeah, this is cool, actually.
Okay, so the next step is a very simple one. We're just going to take a little bit of detergent.
I feel like I don't want it to sink.
Wow.
Don't let it sink.
So again, what the detergent is going to do is the water is going to be attracted to the detergent rather than just to the water. And so that's going to reduce the cohesion. And we'll see if the paper clip sinks. So you can just take a little drop, and I'll let you do that if you want, and stick it in the corner.
Like away from the paper.
And one thing that usually happens is the paper clip runs away from it.
No!
Yep. See that?
Oh.
Yeah, so the first thing it did was the paper clip basically went really fast in the opposite
Yeah, it
direction.
went like that.
And then it sank, you know, and
Wow.
all of that was within like less
That was
than 2
dramatic.
seconds maybe.
The water was attracted to the dish.
Exactly, so then it's not cohesive.
Yeah.
Yeah.
Wow.
That was
Oh.
Yours lasted longer than ours. For some reason, I think the water in this bowl wasn't as cohesive, maybe. Which, just for an error analysis perspective, knowing that we eat from these bowls, specifically Isaac does, why might one bowl be less, have water that's less cohesive than another? If we,
there might be something in it.
yeah,
Maybe not. Or it might
Specifically-
already have some soap in it.
yeah,
Washing it.
exactly. So when we run these all through the dishwasher, there might be a tiny bit more soap in one than the other. Yep. And so I kind of think there might have been a little soap residue in this green one up here. Or maybe just a little bit more than in theirs.
So we just drop it in the water?
Mhm.
Our toilet paper kind of safe.
Okay.
Charles killed it though. Doesn't even move.
Yeah, so this one up here took like 2 seconds or less. Yours, I don't remember how long yours was longer, but yeah, you guys were longer, like, 3 to 5
Just like
seconds.
moved out of the way, stood there, and then dropped.
Yeah, what about you three?
Ours is
Pretty much instantly dropped?
Yeah.
Nice.
Why was it entertaining though?
Yeah, I don't know.
Actually.
Well, why are you guys so excited about me bringing balloons to last class? I mean,
Yeah, there's still a balloon here. I just don't know where it went. Oh, there it is.
oh, good. Okay. All right. So there's one other. This is the only part of the experiment you have to write a lab report on. Let's do another part to it though. Actually, you know what? Let me think about this because the other one could kind of work as control a little bit. Nah, you just have to write on this
How
one.
long
That's
do you
fine.
think it was before the toilet paper stain? It took
Because
like
this
a
next part
second.
is optional, so I'll just leave it like that. The way it's optional.
Well, the second time we
All
put
right.
it on the toilet paper for this.
So we're gonna do another test.
Oh, how long it took for the toilet paper?
And the way we're going to do this test, can I get a volunteer to empty and wash this out, please? All right, Bo, you're here at the front.
Yeah.
So, just this, Bo. Yep, and I'll take the paper. Wash the paper clip too, but I'll take it back. I don't need the toilet paper.
So were you saying something about the lab report for this?
Yeah, so write a lab report on everything we've done up to this point, and everything we do after this point, you don't have to. Okay?
Whoa.
Yep,
Actually, I kind of like that.
that's good. Well, if you go into a
That
science
is good.
degree, you'll have to do
When they, have, like, our waters, when there tends to be,
You have to move it.
like, a result that
Who has the giant scissors?
it didn't, what I'm trying to Yeah, they just were like here, if one of it worked, like the book said it should have, they write the report based on what happened instead of the one at their table.
That's okay with me, yeah.
No,
So,
no,
when you're writing your lab report,
Boys,
if yours didn't work very well, but somebody else's did, then, one thing you might say is like, our particular test, did this, but the other test did such and such. Like, you can kind of steal somebody else's results like that if you want. That's just a good way to, if you feel like it's easier to write based on successful results, then that's something you should do. All right, so when Bo gets back, what we're going to do is we're going to something that is not polar, something non-polar, and try the same experiment with it, where we're going to try to float. Thanks, Bo. So vegetable oil, thank you. Have you ever noticed that oil and water don't mix? I'm sure you have.
Yeah.
And you see it like too with like salad dressings, like the vinegar, the water, whatever's in it, and the oil, they don't mix. They kind of separate out and you have to shake them. So especially like an Italian dressing would be a good example. That's where it gets real separated. So oil is non-polar. It's not going to have any kind of imbalance of charges. It's just going to be like a totally non-charged substance. So do you think there's going to be much cohesion in the oil?
Yes.
And like thus, much surface tension. So yeah, so the thing that causes the cohesion and the surface tension, which is just, again, cohesion on the surface, is the electromagnetic attraction between the water molecules. But if you have something that doesn't have any kind of a charge, then there's going to be no positive and negative sides to attract to each other. And the result is going to be that it's going to be like, you put this cow on this bridge and it just falls through. Like nothing holding it up.
Okay.
Or we'll see if that happens. All right, so here's the vegetable oil, or canola, I guess. I'm not going to totally fill it just so as not to waste it. That's still in the shot pretty well. Good. All right, yeah, if you just want to tear that in half, I don't think we have to be very precise on this one because we're not writing on it. Very good.
So this won't be in our lab report?
Yeah, you don't have to put this in. I mean, I won't count off if you do put it in, but it's not required because this is an optional stage of the experiment according to the book. So
So we're still doing
no,
we're still doing a full lab report with everything. We're just not including this part of the experiment.
exactly. Yeah. So still doing a lab report on everything we did before this point. All right, thank you. Now,
I think if you do the flip the other way, it might.
yeah, I think you're right. Okay. So let's see if this will float in the first place. It's holding up the toilet paper really well.
No, it looks like it's gonna.
Is it starting to go?
I think so.
And one of the ways you can kind of tell if something has a good surface tension is see if you can see the surface bending under the weight of whatever is on top of it.
Not really bending as much as it did with the water. It's just like
Yeah,
staying
definitely not.
close. I was just staring at it.
May have to help it along, depending on how much time we have left. We got 5 minutes, so I'll help it along.
How do you help this?
If I get another paper clip and poke it. Who had the elephant paper clip, by the way? Yes, you're lucky.
Oh, oh, it sunk.
I was serious.
Sinking.
Oh, good, good.
It just like the entire thing.
Oh, yeah, okay, so when it sank, everything went down under it. And we could, if we're being really scientific, should we try that again multiple times?
Yes.
Yeah, especially because with the water, we had to do it a couple of times. But I can tell you though, just because we already know this is non-polar, it's not going to have that surface tension which holds things up. And here's a fun fact about all this stuff. You know those little black water beetles that just kind of look like a little bullet or something and they just dart around? They're called whirligigs.
Yeah.
Those are hunted by water striders. And water striders are the spidery looking things that will actually like dart around on the surface of the water. And so as they're hunting the whirligigs have a secret defense. And that is they have their own natural detergent like the soap that we have here. It's
the other ones drown.
exactly. So the whirligig is darting around, the water strider comes up to it, and you can see the water bending under the water strider, but you know where the surface tension is. But then the whirligig will shoot out this orange scented, which is makes it even more like a soap, this like kind of orange scented substance, and then it attracts the water molecules to it instead of each other, and then that's exactly what happens. The water strider will sink and drown.
Right, so technically, if you want to clean dishes,
Mhm.
you just put a whole bunch of those things in the sink and then put one water strike to make them all triggery.
The thing is, I don't know if it's like antibacterial detergent, but it really does smell like oranges, which is so funny. So anyway,
Have you smelled it?
yeah,
Have you been?
because I've caught them as a kid and they've squirted it out at me.
Ew.
I can't remember if it was, and I think it was like a slightly orange color too, but mostly white, just like a little bit orangish. I can't really remember very well though. So yeah, any questions before we end? Now, in the last 3 minutes, let's see, is there anything else I can mention so you're not sitting bored? Because I can't really leave early. Yeah, I guess I could, but
Yeah, talk about that
Yes,
question.
can we play Hangman?
nah, it's not what I'm talking about. I'm stuff from the module that I can introduce early. All right, so and water surface tension is going to be unusually strong, but again, when we are actually, oh, I can tell you this. This will be interesting. So I mentioned that pretty much all of water's unique qualities come from. You guys should sit down, please. From its polarity. One of them is. Have you ever noticed that ice will float on water? Of course, you've noticed that, right? So what floats? The denser or the heavier substance? Like, for example, if you took rocks and put it in water, will that float? Yeah, so the heavier substance is going to sink, or the denser one. But ice actually floats. And in general, though, is a solid denser than a liquid?
Yes.
Yeah. So, I mean, if you had like liquid metal of some kind, and then you had solid metal, then the solid metal is going to be denser. But water is the exception. And so that's why ice will actually float on liquid water. And the reason is also because of water's cohesion. So with that polarity and everything, like when you have the water molecules attracting each other, they get really close together because of the positive side attracting the negative side. And so as a result, when you have liquid water that can flow freely and they're in close contact with each other, and so as a result, they'll get really, really packed in. But then when you freeze water, what happens is they get locked in place and they can't get drawn to each other because they're locked in that structure. So so that's why ice is actually less dense than water and it'll float. That's actually really, really important to all life on Earth because otherwise our oceans could freeze and things like that. All right, take care, everyone. Have a great weekend. Bye, Sarah.
Yes.